now. Sorry, I have a sore throat right now, but my channel, there's no specific thing that it's really about, in my opinion. I just do all sorts of stuff. Sorry, my voice really is sore, so I might not be sounding right. So I kind of just do a ton of different stuff. But right now I'm going to be doing something so alien to what I normally do on this channel. I'm going to start explaining stuff. Like Albert Einstein's equation, E equals mc squared. Well, E means energy. And the equation basically means energy is equal to the mass of an object times the speed of light squared. Squared is the 2 symbol here, and I think C represents the speed of light. So energy is equal to the mass of an object, so how many particles / atoms are in that object, times the speed of light squared. And let me explain to you something. The mass of an object, it doesn't always matter the size of an object. Sometimes more mass can be clumped together into a small object, but it still has more mass than a larger object. I can show you an example. So take these 2 marbles. This one is bigger, whereas this one's just smaller. Now normally the bigger one would have more mass just because it's bigger, but the smaller one could still have more mass could still have more mass if the mass was all crammed in there and there were more particles crammed into the small space. And you know what's strange? These 2 marbles here, although one is heavier than the other, they seem to fall at the same rate. Even if you move them apart, they still seem to be falling at the same speed. But let's zoom out a little bit so we can see more. This one eventually starts falling behind it. Now this has to do with a lot of things. One reason might be gravity, but ultimately it's because this one's heavier. Now just because something's heavier doesn't mean it has more mass, so don't start thinking of that. But basically, this is behind this when they all started out the same, because the heavier things tend to sink because they weigh more, so they fall down, whereas this is still falling down, only not as much because it's lighter. Like, for instance, if you were to try to drop a balloon to the ground and at the same time drop a bowling ball would obviously make it to the ground first because it's heavy and the balloon is filled with air, so also it means it would take a really long time. But just some stuff that's a little more realistic, like maybe a volleyball and a bowling ball. Well, obviously that bowling ball is still going to touch the ground first, because once again, it's a lot heavier. So, usually I don't give lots of scientific speeches on my channel, but I'm doing a change. Now, in science class, our teacher teaches us some good stuff, but I'll tell you what I have been taught by her. First of all, I'm just thinking of some good stuff to tell you. Ooh, we're learning about friction and gravity. So, mainly just physics though. The 4 forces are push, pull, gravity, and friction. Now, the definition of motion is a change in an object's position. And an object in motion will remain in motion until acted on by a force. And in our case, it's gravity. Like, say you throw a football of some sort. If there were no gravity, it would remain in motion forever. But gravity is the opposite force pulling down on it. Like, for instance, let's pretend this is your football here. We throw you. It just keeps going up and up and up. But gravity is slowly pulling it back down to the ground. Now, I could kind of show you an example of what it would be like without gravity, because Algodo offers possibilities like that. Just trying to find my... Holy! Holy gods, my roast is ruined! So... gonna try to find... material. Helium. You see, what it would be like if no force acted upon this. It would just keep on going up forever because gravity isn't acting upon it. Whereas if I go like, let's see, material. Default, it will eventually start sinking. So, yeah. And you can sort of do the same thing in reverse. An object at rest will stay in rest until acted on or acted upon by a force, like a push or a pull. So, let's say, I'll just make another marble. Let's say this marble here, geometry actions, glue the background. This marble is at rest. I mean, if nothing touched it, it could probably remain there forever in real life. But eventually, you know, someday, something's going to act upon it. So it could remain at rest forever until, of course, somebody touches it or hits it. Or a good experiment to try with this one is actually a paper cup or all you're going to need for it is a paper, a small piece of paper, a cup, and something like a quarter or a nickel, preferably a nickel though. And what you do is you put the small piece of paper on top of the cup, and then you put the quarter or whatever it is on top of that piece of paper. I could actually demonstrate that experiment right now. Oh, come on. So that will be our piece of paper, and then the cup. We by 3 trees from yonder glen do spy a maiden fair and sweet. Now, this, let's do loosen. Dang it. Let's rotate you. So as you can see, it actually is moving, but we don't really want it to move in real life, so we're going to have to make amends to that by making both sides pretty much even. Now, as you can see, it isn't moving much, but what you're supposed to do is it will remain at rest until motion is acted upon it, or until some sort of force is acted upon it, and then once it's in motion, it will remain in motion until a force acts upon it. Now, that's basically what the experiment does. The piece of paper flies out, whereas the object goes in, but it also has to do with the fact that since basically the nickel or whatever is a lot heavier and the piece of paper is like a lot lighter and it's basically the same thing as when people like pull the tablecloth off of the table and all the food stays on. Well, it's like that. The reason that the nickel or whatever you use doesn't move is because or doesn't change position is because basically it's heavier, first of all, and second of all, if you pull it fast enough, it doesn't have enough time to stick on. And friction, ooh, we've got to talk about friction. Ooh, if only there was ice in, oh, actually, I think there is ice in Algodoo. This is going to be a real treat. Feel your heart beat to the beat of the drums. Ice. As you can, oh, gotta glue you. I swear to God. Why is it always slanted? I feel like that's the perfect line. For God's sakes, Algodoo, make it easier to draw a straight line. Don't. But as you can see, when it's ice, it slides on it for longer. And you know what? We're probably going to need to make a bigger thing for it to work like this. Feel your heart beat to the beat of the drums. Now, once we give it a push, since it's ice, it's going to stay on it for a since ice is slippery. You know, when you're on ice, you gotta stop going somehow. And that's where you've got friction. Friction comes in to help you. Friction comes in to save the day. Just when you think you can't stop. Probably should make this track longer. I just realized. See how it's eventually slowing down even if I make this really long. Geez, actually it might not slow down here. I think it's because of the ice. But whatever. Oh, come on, don't freeze on me, Algadoo. You froze on me just like the ice. Oof. Here we go.